MOSFET is a very popular semiconductor switch, especially for DC-DC converter. We'll discuss its drive. Let me draw the MOSFET symbol. So this is called the gate and is called the drain. The substrate and the source are connected. So you have the drain, source, gate. There is a natural internal body diode. The arrow here pointing to the N-channel inversion layer that will get formed. So this is an N-channel MOSFET. The MOSFET is a high input impedance device, meaning it takes a very, very low gate current, unlike the case of the BJT. So the gate power requirement for the MOSFET is very low. It is more a voltage control device as compared to the BJT, which is a current control device. So it is important that we give an amount of charge for the MOSFET as required by the data sheet of the MOSFET. And if you give that amount of charge to the gate source, then that will turn on the device. So you can think of the current, now the ID, which is flowing through the drain current, and then there is internally an equivalent capacitance gate source, let us say, and then you need to put a charge QG into the gate source so that the device turns on. So imagine it in that fashion. So let us look at the drive requirement. So let's say this is the time. I will split it into time zones. This is the off state of the MOSFET. This is the on state of the MOSFET. Again, the off state of the MOSFET. There is an off to on transition. This is called the turn on period. There is on to off transition. This is the turn off or the switch off period. So during this time, let us look at how the gate current IG looks like. So as I said, this is a charge control device, voltage or a voltage control device. It is actually this charge that is important. So therefore, we will see how the gate current looks like based on that argument of giving a specific amount of charge to turn on the MOSFET. So during the off state, no gate current is needed, so that is 0. During the on state also no gate current is needed. In an ideal sense, you need 0 gate current to maintain the switch in the on state, and therefore also finally in the off state 0 gate current. So you see the gate current requirement, how it looks like, almost all 0, 0, 0. The only difference comes in the turn on period and the turn off period. So during the turn on period, you want to switch on the MOSFET. You supply a specific amount of charge called QG as defined in the data sheet for that specific MOSFET. After you supply that charge, the MOSFET will turn on. So let us say I will supply some a current with some profile like this. The area under that curve is the charge QG. Now if I have supplied this QG amount of charge to this MOSFET, then the MOSFET will turn on. The voltage across the MOSFET will be 0. And there is no charge and no current needed to maintain the MOSFET in the on state. So once turned on, it will remain on. That is why we say it is a high input impedance device till you want to turn it off. When you want to turn it off, all you have to do is remove the charge that you have given to it while turning on. So whatever charge you have given, remove that charge and you would have switched off the MOSFET. So this is how the requirement for the gate current will look like. Now as it is a charge control device or a voltage control device, you are actually not so much interested in the shape of the current as long as I am able to give the required gate charge. So you can also give the gate currents in this fashion, a pulse gate current like this. The area under that should be Qg. So as long as I am giving Qg amount of charge, the MOSFET will turn on. Or instead of that, I could give an RC, an exponential decay like this. As long as the area under this is Qg during on time 0, then remove that amount of charge that you had supplied to turn it on. So this is also fine as long as you are giving Qg amount of charge to turn it on and remove Qg amount of charge to switch it off. This is also valid. In fact, this is the type of current wave shape that we will see mostly, because it is much easier to put an RC drive circuit rather than trying to achieve constant current in a constant current pulse drive circuit. This is typically the behavior of the MOSFET, the dynamic behavior of the MOSFET. You need to supply the MOSFET at the gate to source, some fixed amount of charge Qg, which will turn on the device. If I am supplying this Qg in shorter time interval, then it will turn on faster. If I am supplying Qg over a longer time interval, then the turn on will be slower. Likewise for turn off also. Let us now see how the basic or the fundamental gate drive for the MOSFET looks like. It is very simple. It consists of only one component, that is one resistor. So let us start from the requirements, the gate drive requirements. I have this timeline. I have split the timeline into the off state, the turn on period, the on state, turn off period, off state. So we have just seen how the gate current looks like. Gate current is 0 during the off state, and let us say it rises and there is an exponential decay where it pumps in a positive gate charge Qg into the MOSFET gate, turns on the device, and then after that you don't need any current to maintain the device in the on state. Then when you want to turn it off, you have to remove the gate charge and then bring the device to the off state. So let us say this is Ig plus and this is Ig minus, and the average of this in the turn on period, we can call that one as Ig average. And if I take a straight line approximation, it is approximately equal to Ig plus by 2. Let me call this period as T on. Let me call this period as T off. So now let us draw the gate drive circuit. So you have the Vg, the gate pulse being given at this point. Then you pass it through a resistor and connect it to the gate of the device. The drain of the device is connected to the external load, and it is the drain current that you want to switch on and off. And the source you connect it to the ground. There is an internal equivalent capacitance which is going to absorb the charge that you are going to pump in. We will call this Vg and this is R1. So how to calculate R1? Very simple. During the time when you want to turn it on, at the time of turn on dynamics, capacitor is a short. So the current that is going to flow through will be the full VCC by R1 or Vg by Ig plus. So whatever this Ig plus is decided, then Vg by Ig plus is the value of R1. And Vg normally is the pulse amplitude, which is VCC of the control gate drive. Now what is Ig plus? Now look at this drive requirement. You take this average. The charge in this period to turn on the device is Qg obtained from the data sheet, and that is equal to Ig average into T on. T on is the designer requirement, how soon or how fast you want it to turn on, and during that period I should have given the complete Qg to the MOSFET. So Ig average into T on will be Qg, and Ig average is approximately Ig plus by 2, and therefore Ig plus is 2Qg by T on. So this can be the value of Ig plus. You plug it in here and then you can get the value of R1. Vg, you substitute VCC, control power supply voltage. So if you actually give a pulse like this, you can expect a current here, gate current here to flow something like this in this like a differentiated differentiated value of this square pulse. So whenever you have a discontinuity here going from low to high, you will get a positive current spike due to this RC, and this will decay as the capacitance here charges up to plus minus, and then when you want to remove it, bring this to ground. Here you are making it 0, and the Vg should have sinking capability. There should be current being capable of flowing in the negative direction. So whatever charge is there in the capacitance, internal capacitance will discharge through R1 and the external Vg circuit. So therefore you get this negative pulse and charge removal. So this way the MOSFET will be turned on and off. Remember, you need some charge to turn on the MOSFET. You don't need charge to maintain the MOSFET in the on state. You don't need charge to maintain. You don't need a gate current to maintain the MOSFET in the off state. You need only current for turning on, and you need current to flow in the opposite direction for turning off. And it is a charge control device. It is very, very important to see that the area under this curve is equal to Qg as declared by the data sheet for that MOSFET, so that that MOSFET can turn on. So this is the simple basic building block gate drive for the MOSFET, and all complex MOSFET gate drives are built using just this. So this is a 1 resistor gate drive. Just like in the case of the BJT, you had a 2 resistor gate drive as the basic gate drive. In the case of the MOSFET, a 1 resistor gate drive is the basic drive for the MOSFET. Let us discuss another MOSFET drive, gate drive, with buffers, CMOS buffers. This can improve the turn on speeds and turn off speeds. Let us see the circuit. I have the MOSFET here. The drain is connected to the external circuit, and the drain current is what you need to control, switch on and off. The source, as usual, is connected to the ground, the ground based gate drive. There is an internal body diode, and the gate is connected to the resistor, the 1 resistor gate drive. And now here you apply the gate drive pulse in the normal 1 resistor gate drive. So when you apply the gate drive pulse, you have the charge being pumped into the gate and that MOSFET turns on. But the turn on time is decided by the amount of Ig plus that can be drawn at that given instant of turn on, and that is dependent on the sourcing capability of the source. If the sourcing capability of the source is low, then even if you reduce this resistance, the charge that will be pumped into the gate will be over a period of time, and therefore turn on time may be longer. The turn on may be slower. In order to speed this up, we can use a buffer. I could use a non-inverting buffer like this. Typical non-inverting buffers like the CD, CMOS buffers 4050. This is a typical non-inverting buffer which can sink 5 milliamps and source slightly more than 1 milliamp. Or you could use an inverting buffer like the CD 4049 and apply Vg at the input. So when you apply an inverting Vg pulse, you will see that when the pulse goes low, the buffer output goes high and then pumps in the gate charge and turns on the MOSFET. Now, in order to improve the speed of turn on, You can put more buffers in parallel. If I erase there and then make some space, let's say I put one more buffer here, and then let's say one more buffer here, connect them in parallel in this fashion. In fact, I can put many more buffers in parallel. So normally the CD 4040, 4050 and 4049 series come as hex buffers. So there will be 6 buffers in a pack, and then you can connect all 6 of them in parallel, and then you can effectively get close to 10 milliamp sourcing, and then you can get around 30 milliamp sinking capability. So the idea here is that now you enhance the sourcing capability of the input. So therefore, by decreasing R1, you will be increasing the Ig plus value, and therefore more gate charge can be given in a given time, or you could say the same amount of gate charge can be given in a lesser amount of time, and therefore T on can be reduced. This is evident by the equation that we saw here. Ig plus is 2 Qg by T on. So as Ig plus increases, T on can reduce. So in this way, you can improve the speed of turn on and turn off. So this is one interesting speed up gate drive for the MOSFETs. All BJT drive circuits can be used for MOSFET gate drive. Let us see an example. I will draw the MOSFET, drain connected to the external load, source connected to the ground, there is a body diode, and we need to monitor ID, switch the drain current. The gate drive is the one resistor R1. Now the source for this gate is coming from the BJT drive circuit, and you can adjust the sourcing and the sinking capability to whatever value of Ig plus you would like to give to the gate drive of the MOSFET. So therefore, with BJT drive circuits, stage by stage you can enhance the Ig plus value to get faster and faster turn on and turn off speeds. So at this point, let me put an NPN PNP combination totem pole directly across VCC, and let me connect both the bases together, and let me drive these bases with a 2 resistor base drive circuit, which we are familiar with, and the drive for this is coming from, let us say, a PNP stage. The PNP stage gets its base drive from another 2 resistor drive stage, which is driven by an NPN stage, which is driven by another 2 resistor drive stage. So you see, like this, stage by stage, the current starts decreasing. The current here, the Ig plus, whatever requirement here will be lesser here on the base side of this. On the base side of the PNP, it will be still further lesser here, till at the source VB, it can be of the order of microamps to milliamps. So let us say we need to give a pulse in this fashion here. Let us say this is Q1, R1, Q2, Q3, Q4. We have 4 transistors. So whenever VB is low, there is no drive current flowing through this resistor path, no base drive for Q4. Q4 is off. When Q4 is off, there is no current in this path, therefore no base drive for Q3 base, therefore Q3 is off. Q3 is off, this is off, no base drive current flowing through this path and no base current for this, and Q1 is off. So when Q1 is off, there is no drive current to charge up the gate of the MOSFET. So the MOSFET is off. So when VB is low, MOSFET is off. ID is 0. Now when VB goes high, there is a drive current flowing through this 4 times, 2 times IB on, and IB on flows through this, and IB on into Q4, Q4 is on. When Q4 is on, there is an IB, there is 2 IB on flowing through this resistor corresponding to Q3 base drive. There is an IB on here, there is an IB on here, Q3 is on. When Q3 is on, there is a drive current flowing through this path into Q1, and Q1 is on. Q1 is on, VCC minus VCSAT appears here, and it will drive a current through R1 into the gate source capacitance of the MOSFET and charge up the capacitance. So QG amount of charge will be pumped in and the MOSFET will turn on. So in this way, the MOSFET will be switched on and off. The value of Ig plus can be controlled by having the number of stages. So the more number of stages means I can have more amplification. So let us say at this particular point you have a 10 milliamp sourcing capability. It could become hundreds of milliamp sourcing capability at this point. It can increase by another factor of HFE SAT here. So you can get in terms of amps. Another factor by HFE SAT you can get in terms of tens of amps. So you can get really very high sourcing capability at this point when you are having multi-stage BJTs to amplify whatever the current here to a large value of Ig plus. So once the Ig plus is very large, you can charge up, you can give the gate charge for the gate capacitance of the MOSFET in a very short time. So the turn on times can be really small. Likewise, the turn off times can also be really small because you will be discharging through these high current devices. So this is a high speed MOSFET gate drive circuit using BJTs. Like you had isolated base drive for the BJT, where the power side and the control side were physically isolated, galvanically isolated. Even in the case of the MOSFET, we can have galvanically isolated gate drive circuit. Now we saw the BJT based gate drive circuit, where the MOSFET is driven by this Q1, Q2 totem pole BJTs, which is driven by Q3 and which was driven by an NPN stage. Now this NPN stage, I will replace it with the NPN BJT of an optocoupler. The optocoupler, where this transistor is being driven by the light emitted from a photodiode. So let me ground this and then connect the pulse source to this optocoupler diode in this fashion, and we have VB, the pulse source, here. So observe here, when VB is 0, there is no drive current to the optocoupler, diode current is not there, diode will not emit photons, and the optocoupler transistor is off. So when this is off, there is no drive current here, Q3 is off. When Q3 is off, there is no drive in this path, and therefore Q1 is off. When Q1 is off, there is no drive to charge up the capacitance of the MOSFET, and therefore the MOSFET is off. So when VB is low, MOSFET is off. When VB is high, there is a drive current flowing through the diode, and the diode emits light, and the optocoupler transistor is on. There is a drive current here. Q3 is on. Q3 allows drive current to flow through in this path to Q1. Q1 is on, and Q1 is on. There is a drive current to charge up the capacitance of the MOSFET, and the MOSFET turns on. When you want to switch off the MOSFET, you are switching off. The pulse here goes low. This is off. This is off. Q3 is off. Q1 is off. But there is a charge on the capacitor here, plus minus. So that is coming to this point, the emitter of Q2. The base of Q2 is low, and because the emitter of Q2 is positive, Q2 will turn on, and because Q2 turns on, there is a reverse current flow in this fashion and discharges the gate charge capacitance. So this is the discharge path and turns off the MOSFET. So this is an isolated gate drive circuit for the MOSFET. Remember, the power side are having different grounds. The control side is having a different ground. And just like in the case of the BJT, you need to have a power supply with isolated secondary windings, and one winding is used for generating the power supply for the power side, and another winding is used for generating the power supply for the control side. So in that way, total isolation, galvanic isolation is maintained between the power side and the control side, and the optocoupler gives an isolation of 3000 volts between the two sides. Like in the case of the BJT base drive we discussed with transformer isolation, the MOSFET base drive can also be done with transformer isolation. Similar circuit. Let me draw that. So the primary of the transformer is connected to an NPN transistor, and the NPN transistor is driven by a 2 resistor drive, which we are familiar with in this fashion. Observe this is NPN transistor which I am using here can also be done with replaced with a MOSFET. Now the secondary of the transformer is passed through a diode, like in the case of the BJT drive, and it is connected to the power MOSFET. The power MOSFET is connected in this fashion, drain connected to the external load, source is connected to some other point in the power circuit. The transformer non-dot end is connected to the source, and the dot end to the diode, and the diode is connected in series with the resistor in this fashion. So this will be a 1 resistor drive for the MOSFET. Let us name the parts. This is R1, this is D1, VCC, Q, R3, R4, and this is VB, the base drive pulse given at this point. So when the base drive pulse VB is high, so you will have a current flow through R3. There will be a base drive current for Q. Q will be on. When Q is on, the transformer primary is active with dot end positive. Dot end positive means on the secondary side dot end positive, and there will be a drive current flowing through D1 R1 to charge up the MOSFET, and the MOSFET will turn on. So as long as the dot end is positive, the MOSFET will be on. Now when VB goes low, there will not be drive current through R3. Q is off, and here the dot end becomes negative, non-dot end becomes positive. The diode will be reverse biased and it will clip the waveform. However, the MOSFET has MOSFET capacitance. There is no discharge path for the MOSFET capacitance, so it will not turn off. So you have to provide a discharge path for the MOSFET. So therefore we will put a resistance here, R2. Only then now the MOSFET can turn off. There is a discharge path. Also note on the primary side, we will put a diode resistor combination like this, the freewheeling diode and the freewheeling resistor. This is necessary to demagnetize the core so that it is ready to operate in the next cycle. So this is the transformer isolated drive for the MOSFET. In the transformer isolated gate drive shown here, there is not much control in speeding up for the turn off of the device because the presence of R2. You can't make R2 too low, because if the R2 is made too low while turning on, R1, R2 becomes an attenuator. So if you are applying 15 volts here, you can have a very low voltage applied at the gate source, and the MOSFET may not go into full enhancement. It may be in the linear region. Therefore, it is better to replace R2 and have an active pull down to speed up the turn off process. So let us do that modification. So I will remove this, make some space and connect it here, and here I will put an active pull down circuit. So let me use a diode and a PNP transistor in this fashion. I will put a resistor here and connect the base to this point. Now let's see how this operates. Now here there is an internal capacitance, remember, so we will have the gate source capacitance indicated by this grade line here. Now let us look at the waveform at the secondary when VB is having a pulse wave shape and in this fashion. Whenever VB is low, Q is off, and whenever VB is high, Q is on. So let us say VB is high, Q is on, dot is positive, dot here will be positive. So you will have a wave shape something like that. And then when here VB goes low, Q turns off. So when Q turns off, there is a freewheeling action happening here. So the voltage exponentially will start coming down. So negative, it will go negative and start exponentially coming down. Remember that this area, positive area, negative area should always balance out. Volt second balance is always valid. So you will have a wave shape like this going negative. That is why we have put this diode D1, and on this side the diode will clip it and will give you a nice neat positive, only the positive pulse. Okay. So during the time when it is positive, there is a current flow like this, and this second diode that we have put will have a polarity plus minus forward drop of 0.6 in this fashion. So there is a current flow and it will flow through R1 and charge up the CGS capacitance. So a charge of QGS is deposited in the MOSFET and the MOSFET will turn on. So during that time when you are driving the MOSFET on, diode is plus minus in this fashion. Look at the PNP transistor. Emitter is minus, base is plus, so this transistor is off. So it is out of the picture. Now after this is on and then you decide to switch off the MOSFET, you bring VB low. So when VB is low, you are in this portion of the region, that is in this portion of the region of the pulse. So let us say that at this point capacitance is fully charged to VC, whatever this peak value, VCC value, and diode is now not conducting. This capacitance potential appears here. Emitter is positive. This is at zero potential with respect to this. There is no current flow. So therefore, there is a possibility of base drive to flow in this fashion. The emitter is positive because of the capacitor. So you will have a base drive flowing in this fashion here. It cannot go in this direction because of the diode. So it has to come in this direction and complete the circuit. So if the base drive flows, then the transistor Q can be on and you can have a larger collector current to flow in this fashion and discharge the capacitor. So the capacitor, in fact, the charge gate source capacitor, in fact, makes this active pull down work. So this is a much better circuit, much faster turn off can be achieved with this.